The point-to-point protocol over Ethernet is a network protocol for encapsulating PPP frames inside Ethernet frames. It appeared at the turn of the century, in the context of the boom of the DSL, as the solution for tunneling packets over the DSL connection to the ISP's IP network, and from there to the rest of the Internet. A 2005 networking book noted that most DSL providers use Pppoe, which provides authentication, encryption, and compression. Typical use of Pppoe involves leveraging the PPP facilities for authenticating the user with a username and password, predominantly via the PAP protocol and less often via CHAP. On the customer premises equipment, Pppoe may be implemented either in a unified residential gateway device that handles both DSL modem and IP routing functions, or in the case of a simple DSL modem, Pppoe may be handled behind it on a separate Ethernet-only router or even directly on a user's computer. More recently, some GPON-based residential gateways also use Pppoe, although the status of Pppoe in the GPON standards is marginal. Pppoe was developed by UUNET, Redback Networks and Routerware, and is available as an informational RFC 2516. In the world of DSL, Pppoe was commonly understood to be running on top of ATM as the underlying transport, although no such limitation exists in the Pppoe protocol itself. Other usage scenarios are sometimes distinguished by tacking as a suffix another underlying transport. For example, Pppoe, when the transport is Ethernet itself, as in the case of Metro Ethernet networks. Pppoe has been described in some books as a Layer 2.5 protocol, in some rudimentary sense similar to MPLS because it can be used to distinguish different IP flows sharing an Ethernet infrastructure, although the lack of Pppoe switches making routing decisions based on Pppoe headers limits applicability in that respect. Original rationale: in late 1998 the DSL service model had a chicken and egg problem. ADSL technology had been proposed a decade earlier. Potential equipment vendors and carriers alike recognized that broadband such as cable modem or DSL would eventually replace dial-up service, but the hardware faced a significant low-quantity cost barrier. Initial estimates for low-quantity deployment of DSL showed costs in the $300 to $500 range for a DSL modem and $300 per MO access fee from the telco, which was well beyond what a home user would pay. Thus the initial focus was on small and home business customers for whom a T1 line was not economical, but who needed more than dial-up or ISDN could deliver. If enough of these customers paved the way, quantities would drive the prices down to where the home-use dial-up user might be interested, more like $50 for the modem and $50 per MO for the access. Different usage profile: the problem was that small business customers had a different usage profile than a home-use dial-up user, including connecting an entire LAN to the Internet, providing services on a local LAN accessible from the far side of the connection, simultaneous access to multiple external data sources, such as a company VPN and a general-purpose ISP, continuous usage throughout the workday, or even around the clock. These requirements didn't lend themselves to the connection establishment lag of a dial-up process, nor its one computer to one ISP model, nor even the many-to-one that NAT plus dial-up provided. A new model was required. Pppoe is used mainly either with Pppoe-speaking Internet DSL services where a Pppoe-speaking modem router connects to the DSL service. Here both ISP and modem router need to speak Pppoe, or when a Pppoe-speaking DSL modem is connected to a Pppoe-speaking Ethernet-only router using an Ethernet cable. For such two-box systems, DSL modem plus Ethernet-only router, Pppoe is now the preferred solution. Time to market: simpler is better. A problem with creating a completely new protocol to fill these needs was time. The equipment was available immediately, as was the service, and a whole new protocol stack would take so long to implement that the window of opportunity might slip by. Several decisions were made to simplify implementation and standardization in an effort to deliver a complete solution quickly. Reuse existing software stacks: Pppoe hoped to merge the widespread Ethernet infrastructure with the ubiquitous PPP, allowing vendors on both sides of the connection to heavily leverage their existing software and deliver products in the very near term. Essentially all operating systems at the time had a PPP stack, and the design of Pppoe allowed for a simple shim at the line encoding stage to convert from PPP to Pppoe. Simplify hardware requirements. Competing WAN technologies required a router on the customer premises. Pppoe used a different Ethernet frame type, which allowed the DSL hardware to function as simply a bridge, passing some frames to the WAN and ignoring the others. Implementation of such a bridge is multiple orders of magnitude simpler than a router. Informational RFC 2516 was initially released as an request for comment status informational RFC for the same reason. The adoption period for a standards track RFC was prohibitively long. Success. Pppoe was initially designed to provide a small LAN with individual independent connections to the Internet at large, but also such that the protocol itself would be lightweight enough that it wouldn't impinge on the hoped-for-home usage market when it finally arrived. While success on the second matter may be debated, Pppoe clearly succeeded in bringing sufficient volume to drive the price for service down to what a home user would pay. It remains the dominant DSL connectivity mechanism as of 2011, more than a decade later. Pppoe stages. The Pppoe has two distinct stages, Pppoe Discovery. Since traditional PPP connections are established between two endpoints over a serial link or over an ATM virtual circuit that has already been established during dial-up, all PPP frames sent on the wire are sure to reach the other end. But Ethernet networks are multi-access where each node in the network can access every other node. An Ethernet frame contains the hardware address of the destination node. This helps the frame reach the intended destination. Hence, before exchanging PPP control packets to establish the connection over Ethernet, the MAC address of the two endpoints should be known to each other so that they can be encoded in these control packets. The Pppoe Discovery stage does exactly this. In addition, it also helps establish a session ID that can be used for further exchange of packets. PPP session. Once the MAC address of the peer is known and a session has been established, the session stage will start. Pppoe Discovery. Although traditional PPP is a peer-to-peer protocol, Pppoe is inherently a client-server relationship since multiple hosts can connect to a service provider over a single physical connection. The discovery process consists of 4 steps between the host computer, which acts as the client, and the access concentrator at the Internet service provider's end acts as the server. They are outlined below. The 5th and last step is the way to close an existing session. Client to server, initiation, PADI stands for Pppoe Active Discovery Initiation. If a user wants to dial up to the Internet using DSL, then his computer first must find the DSL access concentrator at the user's Internet service provider's point of presence. Communication over Ethernet is only possible via MAC addresses. As the computer does not know the MAC address of the DSL-AC, it sends out a PADI packet via an Ethernet broadcast. This PADI packet contains the MAC address of the computer sending it. Example of a PADI packet. Frame 1, Ethernet 2, SRC, 0050 DAR 42D7, DF, DST, FFFFFFFFFFF, PPP over Ethernet Discovery, version 1, Type 1, Code Active Discovery Initiation, Session ID, 0000, Payload Length, 24, Pppoe Tags, Tag, Service Name, Tag, Host Unique, Binary Data. SRC holds the MAC address of the computer sending the PODI DST as the Ethernet broadcast address. The PADI packet can be received by more than one DSL-AC. Only DSL-AC equipment that can serve the service name tag should reply. Server to client, offer, PADO stands for Pppoe Active Discovery Offer. Once the user's computer has sent the PADI packet, the DSL-AC replies with a PADO packet, using the MAC address supplied in the PADI. The PADO packet contains the MAC address of the DSLAC, its name and the name of the service. If more than one POP's DSLAC replies with a PADO packet, the user's computer selects the DSLAC for a particular POP using the supplied name or service. Here is an example of a PADO packet. Frame 2, Ethernet 2, SRC, 000E, 47B, F38A, DST, 0050 DAR 42D7, DF, PPP over Ethernet Discovery, version 1, Type 1, Code Active Discovery Offer, Session ID, 0000, Payload Length, 36, PPPoE Tags, Tag, AC Name, String Data, IPS rule, Tag, Host Unique, Binary Data. AC Name String Data holds the AC name, in this case a EUROEIPZBR001 a Euro SRC. Holds the MAC address of the DSLAC. The MAC address of the DSLAC also reveals the manufacturer of the DSLAC. Client to Server, Request, PADR stands for PPPoE Active Discovery Request. A PADR packet is sent by the user's computer to the DSLAC following receipt of an acceptable PADO packet from the DSLAC. It confirms acceptance of the offer of a PPPoE connection made by the DSLAC issuing the PADO packet. Server to Client, Session Confirmation, PADS stands for PPPoE Active Discovery Session Confirmation. The PADR packet above is confirmed by the DSLAC with a PADS packet, and a session ID is given out with it. The connection with the DSLAC for that POP has now been fully established. Either end to other end, termination, PADT stands for PPPoE Active Discovery Termination. This packet terminates the connection to the POP. It may be sent either from the user's computer or from the DSLAC. Protocol Overhead, PPPoE has the highest overhead DSL delivery method. On ATM DSL, the amount of overhead added by PPPoE on the DSL side of things depends on the packet size because of the absorbing effect of ATM cell padding which completely cancels out overheads of PPPoE. In some cases, the PPPoE overhead can cause an entire additional 53-byte ATM cell to be required, and IP fragmentation can be induced. However, ignoring ATM and IP fragmentation for the moment, the basic additional protocol header overheads for AAL5 payload are typically 2 bytes plus 6 plus 18 plus 10 equals 36 bytes. For very small packets this overhead is even greater because of Ethernet frame padding. However, more realistically, the typical DSL ATM overhead is either 0 or 53 bytes as in case where the ATM cell payload maximum of 48 bytes is exceeded, so requiring an additional 53-byte cell. The 36-byte figure deduced earlier can be slightly reduced by various means. Discarding Ethernet FCS loses another 4 bytes, for example, bringing the total down to 32. Compare this with a vastly more header-efficient protocol, PPPoE, with a fixed 10-byte overhead inside the AAL5 payload. On Ethernet, on the Ethernet side of things, additional overhead for PPPoE is a fixed 2 plus 6 equals 8 bytes as before, unless IP fragmentation is produced. MTU-MRU, when the DSL modem sends and receives PPPoE containing Ethernet frames across the Ethernet link to the router, there is an overhead of 8 bytes added within the payload of the Ethernet frame. This added overhead usually means that a reduced limit of 1492 bytes is imposed on the length of IP packets sent or received, as opposed to the usual 1500 bytes for Ethernet networks. Some devices support RFC 4638, which allows a 1508-byte L Ethernet frame, sometimes called a Euro Baby Jumbo frame is a Euro unregistered trademark, thus allowing a full 1500-byte payload to be transported over a PPPoE session. This is advantageous because of the many companies who block all ICMP traffic from exiting their network. This stops path MTU discovery from working correctly and can cause problems for people accessing these networks with MRU of less than 1500 bytes. How PPPoE fits in the DSL Internet Access Architecture. The transport protocol used on the telephone network is ATM. The DSL modem encapsulates PPP packets inside ATM cells and sends them over the WAN. There are several encapsulation methods. Pppoe to Pppoa. In this diagram, the scenario is the same as before with two exceptions. A more efficient modem architecture is shown, the modem being a Pppoe to Pppoa protocol converter. The service provider offers a Pppoa service and does not understand Pppoe. There is no Pppoe in this protocol chain. In this alternative topology, Pppoe is merely a means of connecting DSL modems to an Ethernet-only router. Here it is not concerned with the mechanism employed by an ISP to offer broadband services. When transmitting packets bound for the Internet, the Pppoe-speaking Ethernet router sends Ethernet frames to the DSL modem. The modem extracts PPP frames from within the received Pppoe frames, and sends the PPP frames onwards to the DSL AM by encapsulating them according to RFC 2364, thus converting Pppoe into Pppoa. On the diagram, the area shown as a Euro backbone. Euro unregistered trademark could also be ATM on older networks, however its architecture is service provider dependent. On a more detailed, more service provider specific diagram there would be additional columns in this area. Quirks. Since the point-to-point connection established has a MTU lower than that of standard Ethernet, it can sometimes cause problems when path MTU discovery is defeated by poorly configured firewalls. Although higher MTUs are becoming more common in providers' networks, usually the workaround is to use TCP/MSS clamping, or rewrite, whereby the access concentrator rewrites the MSS to ensure TCP peers send smaller datagrams. Although TCP/MSS clamping solves the MTU issue for TCP, other protocols such as ICMP and UDP may still be affected. RFC 4638 allows Pppoe devices to negotiate an MTU of greater than 1492 if the underlying Ethernet layer is capable of jumbo frames. Some vendors distinguish Pppoe OA from Pppoe OE, which is Pppoe running directly over Ethernet or other IEEE 802 networks or over Ethernet bridged over ATM, in order to distinguish it from Pppoe OA, which is Pppoe running over an ATM virtual circuit using RFC 2684 and SNAP encapsulation of Pppoe, which doesn't use SNAP. According to a Cisco document, Pppoe OE is a variant of Pppoe where the Layer 2 transport protocol is now Ethernet or 802.1q VLAN instead of ATM. This encapsulation method is generally found in Metro Ethernet or Ethernet digital subscriber line access multiplexer environments. The common deployment model is that this encapsulation method is typically found in multi-tenant buildings or hotels. By delivering Ethernet to the subscriber, the available bandwidth is much more abundant and the ease of further service delivery is increased. It is possible to find DSL modems, such as the Drake Figure 120, where Pppoe is confined to the Ethernet link between a DSL modem and a partnering router, and the ISP does not speak Pppoe at all. Post-DSL uses and some alternatives in these contexts. A certain method of using Pppoe in conjunction with GPON has been patented by ZTE. Pppoe over GPON is reportedly used by retail service providers such as Internode of Australia's National Broadband Network, Romania's RCS and ADS, or in France and Philippines' Globe Telecom. Verizon's FiOS product uses DHCP in some states and Pppoe in others. RFC 6934 Applicability of Access Node Control Mechanism to PON-based broadband networks, which argues for the use of Access Node Control Protocol in PONs for among other things authenticating subscriber access and managing their IP addresses, and the first author of which is a Verizon employee, excludes Pppoe as an acceptable encapsulation for GPON. The protocol encapsulation on BPON is based on multi-protocol encapsulation over ATM adaptation layer 5, defined in RFC 2684. This covers PPP over Ethernet or IP over Ethernet. The protocol encapsulation on GPON is always IPOE. The 10GPON standard provides for 802.1x mutual authentication of the ONU and OLT, besides the OMCI method carried forward from G984. G987 also adds support for authenticating other customer premises equipment beyond the ONU, although this is limited to Ethernet ports, also handled via 802.1x. There is some modicum support for Pppoe specified in the OMCI standards, but only in terms of the ONU being able to filter and add VLAN tags for traffic based on its encapsulation, which includes Pppoe among the protocols that ONU must be able to discern. The Broadband Forum's Tier 200 using EPON in the context of Tier 101, which also pertains to 10G EPON, says the OLT in the multiple subscriber ONU must be able to perform the Pppoe intermediate agent function, as specified in Section 3.9.2/Tier 101. A book on Ethernet in the first mile notes that DHCP can obviously be used instead of Pppoe to configure a host for an IP session, although it points out that DHCP is not a complete replacement for Pppoe if some encapsulation is also desired, and that furthermore DHCP does not provide authentication, suggesting that IEEE 802.1x is also needed for a complete solution sans Pppoe. There are security reasons to use Pppoe in a shared medium environment, such as power line communication networks, in order to create separate tunnels for each customer. See also, multi-protocol encapsulation over ATM, point-to-point protocol daemon, point-to-point tunneling protocol, point-to-point protocol over ATM, point-to-point protocol over X. References. External links, RFC 2516, a method for transmitting PPP over Ethernet, RFC 3817, Layer 2 tunneling protocol active discovery relay for PPP over Ethernet, RFC 4638, accommodating a maximum transit unit maximum receive unit greater than 1492 in the point-to-point protocol over Ethernet, RFC 4938, PPP over Ethernet extensions for credit flow and link metrics, U.S. Patent 6,891,825 method and system of providing multi-user access to a packet-switched network.